The next section of chapter 5 focuses on molecular geometry. It's essentially electrons repelling each other that are attached to a central atom to make some sort of molecular shape. And in order for me to do that, fair warning, I'm going to switch to the camera, which so that I can show you some molecular models and you can see how things push away from each other. It really helps, but you're going to have to look at me, and it's not a pretty sight. So just want to give you a fair warning. So are you ready? Here it goes. All right. So here I am. Hey, how's it going? Welcome back to chapter 5, almost halfway done. So I'm going to be holding these things up and hopefully that will help. Normally in the lecture, it's really nice and interactive and people can actually hold these up and look at it and if you have a molecular model set, so you should probably use it. But so as I said, what we can have here's a great example, right? So you have a central atom and you have two atoms attached, and it makes sense that these two things attached to a central atom would push away as far as possible, and so make a linear shape, right? And so that's what Vesper theory is all about. It's about looking at regions of electron density and whether you have a bonded lone pair. I mean, this is not a lone pair, but it's two electrons, right? So there are two electrons here making a bond, right? So this is a region of electron density. And so you have two regions of electron density that are attached to a an atom, and then you have two other regions of electron density that are not attached to an atom. But nevertheless, there are a total of four regions, and these four regions repel each other. So that's what we look at when we look at Vesper theory, which stands for valence shell electron pair repulsion rule or repulsion model. Um, it just makes sense, right? So as I showed you before, I showed you a model, and I don't need to show you again. It's pretty easy to envision that when you have two atoms attached to a central atom, that they would go as far away as possible from each other, repel each other to make a 180-degree angle, right? So that's pretty easy. And so uh, and then for three pairs we have and so this is just about the electronic geometry here, right? For the electronic geometry, we don't distinguish between lone pairs and bonded pairs, okay? Just electron regions. So if you have something like BF3, there are three regions. And so here we don't have any lone pairs, so it's indistinguishable, but we have three regions, and so that makes a trigonal planar shape, right? So it's like a triangle, and it's planar. Okay, so let me bring up the model. I already had it up. You can kind of nicely see, looking straight down on it, that this is planar. Not planar, you can see that it's a triangle, and so the planarity comes in if you tilt it to its side. And let's see if I can orient it so you can see that, but this is flat, right? So this is in the plane, and so that's easy to visualize without a model, right? And so, but it doesn't really matter. It's electronic geometry, whether these are bonded pairs or lone pairs, right? So whether there are two atoms here and a lone pair, it doesn't matter. The electronic geometry of this with three things attached is trigonal planar, okay? And so the second example here is SO2, and if we drew that earlier, hey, you switched that far? Oh my, the glitchiness is just making me twitch. Anyway, if you remember, we have here also, oh geez, please stop glitching out on me, man. I paid $300 for this tablet. Anyway, SO2 has a lone pair and two bonded pairs. Right, not pairs, but bonded regions. So they have three regions. So its electronic geometry is also trigonal planar, but its molecular geometry is not. Its molecular geometry is bent. Okay, and that's because lone pairs don't have matter. They just take up space. And so you need to just simply distinguish, but it really helps looking at the regions of electron density and to find out what the actual shape is, right? So if we then look at 4 pairs attached. CH4 is a great example. And if you draw it on paper like this, it looks flat and it looks like there are 90-degree angles here. And for some people, it's hard to visualize that these are still going to push away from each other. They're going to go away as far as possible from each other, and they have not just the paper to deal with, they have an entire third dimension. They can come into the board and back to the board, and that's why you sometimes you see this with these wedged bonds, right, where these two of these hydrogens are, and I'm really sorry about these glitches, they're driving me crazy. It's really going to mess up my wedged bonds now, right? So this is actually 109.5 degrees. And so sometimes we draw, and so one of these hydrogens comes out towards us, and one of these hydrogens goes into the back of the board. And so there are 109.5 degree angles between each of these, right? And so here I have a model, a tetrahedral model, and so this is what it looks like when four atoms or four regions are attached to a central atom and push away from each other, right? If you look down at it like this, if you draw it like this, it looks like it's trigonal, but if you look at it from the side, it's not planar, right? So these all stick up, they go up, and so these angles here are 109.5 degrees, and it's highly symmetrical. No matter how I twist it, right, you have that 109.5 degree angle here, right? So that's four pairs. And so what happens is when you go to NH4, one of these, there's a lone pair here and a nitrogen. I'll draw it in a minute, but one of these simply is removed. It's not removed. It's the lone pair of electrons that push us down, but there's nothing here. There's no matter here. So it's still pushing down, and now the molecular shape is trigonal pyramidal, right? It's not tetrahedral, it's not trigonal planar. It's because of that lone pair pushing down, right? So I'll draw it for you here. So we have NH3, so we have nitrogen. And you're just gonna have to suffer through this. This is really glitchy. It's different software, and plus I'm getting all these streaks here. And so this still has four regions, right? Three hydrogens and a lone pair, so it's four regions. So its electronic arrangement is tetrahedral, but its molecular shape is trigonal pyramidal. And then you take this one step further for water, and you all know that water has also four regions. We've drawn it already, and it's bend, right? So four regions, but only two of them are atoms, so this is bend. See, I'm already way ahead. I'm looking at molecular geometry here, but we will do it all together. So make sure you pay attention to what I ask you on an exam: electronic geometry or molecular, and ultimately molecular is what we are interested in. We're going to move on along to 5, right? 5 things attached is a little unusual. It's called a trigonal bipyramid. Okay, so here we go. This is a trigonal bipyramid, all right. So I'm holding it so it looks like it's trigonal planar. In fact, we have the center, the region in the middle is a triangle, but we also have it capped with two other atoms here. So we have two different regions. We have, and this is called a trigonal bipyramid. So we have two different positions. We have the top and bottom. These are called axial positions, right? Like an axis, axial, right? And they are with 90 degrees to the equatorial position. Okay, so those are in the triangle are equatorial position, and they are 120 degrees with respect to each other, right? 120 degrees. 120, 120. And then these are the equatorial and axial are 90 with respect to each other. And then, of course, if you wanted to look at the two axial ones, that's perfect 120 degrees, right? So we have two different angles here. Let's see, I can draw one. There's no example here, but oh, there's a PCl5. But okay, so and then 6 pairs are an octahedral. So let me just show you the octahedral. you have 6 regions, and these are all 90 degree. This is highly symmetrical now. 6 regions pushing away from each other, and so that's called an octahedral, right? Okay, right. It spins nicely. Yes, that's right. Okay, let's see what we got next here, right? Yeah, I'll talk about this in more detail here, I guess, right? So let's switch over to the next slide, if it will let me. And here I am now focused on 5 regions. We already did the tetrahedral where I was removing a lone pair, an atom, and left a lone pair. We went to trigonal pyramidal, and then we went to bent. And so let's do the same thing here. Now it gets a little bit more complicated. So PCl5, oh, come on. Okay, I meant to do this. PCl5, and I'm going to draw just what's up there. And so you can kind of see here, this is the triangle, and I've left out all of the lone pairs, but they are there and they should be there. And when I ask you to do that, you need to put them in. I can get away with it because I'm the instructor, right? Okay, so that's pretty simple. But now we ask ourselves a question. This is a tricky one. And yeah, it tells you it's going to be a seesaw. So it kind of gives away the answer of what I'm about to ask. But if you draw SF4, and you don't know the shape, but you can draw this. Oh, this is driving me nuts. Okay, so we have 5 regions. We know electronically it is a trigonal bipyramid. But the question is, which one of the atoms is going to be replaced? Is it going to be the axial or the equatorial position? All right, so you need to think about that, and you need to maybe have some more information before you can make that call. So imagine this right here. This is one of the equatorial bonds here, right? Yes, equatorial bonds. There are 2 electrons here holding that atom. If I remove that atom, I'm leaving the electrons. They're going to push down. They're going to require more space. Okay? So, which atom is removed, where the lone pair goes, is determined by how much space is freed up. The lone pair is going to choose the position where it can spread out more, right? Okay, and so most students, and I did the same thing initially, you think that, oh, it's this one here. If you remove this extra, wow, that's a lot of space, right? So you have an entire half sphere that's free, but that's actually not the one that frees up more space. It's actually the equatorial one, and that would be a good one to remember. Every time you remove an atom, the lone pair is going to go into the equatorial position. So removing in the equatorial position, what happens is you not only are freeing up a half a sphere. This is actually a good way to look at it, because the half sphere would be here. You're also gaining this space here, right? You're gaining a little bit more space. So you're going to remove the equatorial position. And so this is why that's called a seesaw. They call that a seesaw here, right? Like a teeter-totter. That's called a seesaw. And now we still have 120 degrees here and 180, but it's a little bit more involved. We'll talk about that in a second here, right? Okay, so we've got that seesaw here. Removing one more lone pair, and so it, by the same logic, oh, that's funny. By the same logic, now if we go to CLF3, if you draw it, and I don't know why my pen wants to do that. Cl, we have 3 fluorines and 2 lone pairs. Okay, so that's 5 regions. And looking at the shape, now this is T-shaped, so you know the answer already. Looking at it here, so you remove another equatorial, and so this makes a T. Equatorial position. It makes a T. Okay? And going to XEF2. That means we're going to do this one more time. And I should know by now that this loves to do that. So xenon. Oh, wow. Fluorine, fluorine, lone pair, lone pair, lone pair. They are all in equatorial positions. So switching back to the camera, if I can find that, get the mouse button here. Okay. So removing one more makes this linear, right? Pretty straightforward. Let's move on to octahedral, right? So might as well stay on the camera, right? So we have an octahedral. They're all equal. It's not a trigonal bipyramid where we have a choice between equatorial and axial. We're just going to remove one that we can. Ooh, these are all kind of tough. All right. So looking at this new shape, molecular shape, this is a square pyramid. Okay, so you can see the square here. Right, I'm trying to locate it so you can see it better. All right, and so we have these 90-degree angles, and then we have this big fat space here, right? So that's the first one. And if another one goes, it's going to go in the opposite. So if we have something that has 6 regions and 2 of them are lone pairs, then this makes a square planar shape. So that was pretty simple, right? So let's switch back here and look at those examples. Oh, now it wants to draw. Okay, that's just fantastic. All right, so SF6 is the example. 1, 2, 3, 4, 5, 6 for a perfect octahedron. And don't forget, formal charges, right? What's the formal charge of sulfur here? Does this make sense? IF5, one of them is a lone pair, and that would be square pyramidal. All right, so we've got these fluorines. And there's a Lewis structure lab that's up. That's a complete dry lab. You don't have to do any, you don't have to take any pictures. You just need to do and practice, and that's going to help you for the exam. And, okay, so we had, okay, I already did SF4 and IF5, and now we're going to do XEF4, and that would be the square pyramid. I want to draw it so you can see it. There's a lone pair on top, a lone pair on the bottom, and then 4 fluorines. So we have 6 regions of electron density. Oh man, I want to curse so badly about that glitch. It's driving me crazy. But I'm trying to pretend that I'm a nice guy. Ooh, I'm giving away all my secrets. Okay, so fair enough. This is good enough for now. We're going to stop, we're going to practice, and then we'll look at bond angles. Oakley dokley.